Hello everyone, this is Dilleswara Rao from my Aeronautical department. So, last few classes we are discussing on automatic control of aircraft topics like displacement of autopilot and control system design and modeling of control systems also we have discussed. So now we will see flight path stabilization. So if you see last class we discussed about the glide slope stabilization also we just discussed like the stabilization thing will be given for you like it will be ask you to make that unstable condition to stable condition only. That means the aircraft will tends to move on stable condition. So here the autopilot system has been asking, I mean it is using for making that aircraft stable only. So on that way so there is a if there is a separate autopilot system is been designed for stabilization thing also, like flight path, how that flight is being moving on cruise condition or maybe in landing or maybe in takeoff condition, how it has been moving on required path and which path it is need to be take also we can design one control system also. So on that way we'll see this topic of flight path stabilization things. So see here, so the two modes of operation of complete longitudinal flight control system has been investigated here for referred to as a Mach hold and altitude hold. So here for stabilizing thing we will discuss on two integrators. So that is Mach hold and altitude hold, because Mach hold will gives you about the velocity thing, and altitude hold will gives you that stabilization thing at a required altitude. So the modes are generally used during cruise operation, and one or other selected depend upon the mission requirement only. So in the Mach hold, the aircraft is made to fly at a constant Mach number by automatically controlling the flight path angle through elevators only, because when if you get the Mach number, the angle given to the elevators, then only that it will get the pitching angle, so that it will get that acceleration. I mean, acceleration anyway will get with the throttle condition, but here the Mach hold is by the constant Mach number, and it will be controlling by that elevator pitching angle also. Like when we are giving that angle input to that elevator, so that elevator will operate it and will gives you the gives you the thing. So for this mode of operation, the aircraft is first trimmed to fly at a steady level, straight level, and then power is adjusted to yield the desired Mach number. So first we need to get that hold, means what it should do. First it has to get the acceleration and get the velocity. After getting the velocity, it should be it will be hold at that place. I mean, it should be hold at getting that velocity. So there the angle of attacks will be mostly will be in a zero condition. If it is a zero angle of attack and without any operation of control surface, means that is a trimmed condition only. So there it will get the required velocity, so that that Mach number thing also it will be automatically it will get. So the Mach fold mode of flight control system is then engaged as aircraft that is generally jet type cruises. The when it is in cruise condition, the fuel is used. The weight of the aircraft is I mean, when the fuel is used, the weight of the aircraft will be decreases, and the speed tends to be increase also. I mean, yes, because we are using the energy, means we are losing that energy also. Like we are using that fuel energy to make that travel in I mean, make it travel in cruise condition. So the increase in speed is sensed by the control system and corrected by an up elevator signal, up elevator signal, causing the aircraft to climb only. Like elevator up signal, if you give, So generally, what will happen for an elevator? If you give the pitching moment, means the elevator need to be up so that it will get the desired pitching angle. So the net result of operation in Mach hold mode is that the aircraft is made to climb slowly as fuel is consumed in order to maintain the constant Mach number, because when at a time acceleration also not needed here. I mean, it's not recommended also. When it is getting slowly, that climbing angle, that pitching, if it is, I mean, the pitching angle, if it is maintained gradually, so that that acceleration also will be maintained gradually. So since the fuel there, the fuel will be fuel also will be used gradual only. So since the fuel consumption of jet aircraft decreases as the altitude increases, so this mode of operation is desirable for long range operation only. So however, there are many times when it is necessary to fly at a constant altitude. So under these conditions, the altitude hold mode is generally altitude hold mode means when it is in cruise conditions, the mode of operation will be like it is giving like it has to hold that altitude mode. So the aircraft flight path angle is controlled by the elevators. Then the airspeed Mach number is controlled. So either the manually or automatically by use of throttle only, because the airspeed we need to control that you already know, because previously that acceleration control system design also, that time we see like while we are giving control of acceleration, we have consider one separate autopilot system for that to give that acceleration with respect to that flight condition only. So for the analysis of two modes like this Mach hold and altitude hold, the transfer function for jet transport is around 600 feet per second, and 40,000 feet are being generally used. So here the altitude control and Mach number control will be like what? Mach hold value will be around the 600 feet per second, and this altitude will be 40,000 feet. So only we will generally use. So for the analysis of Mach hold mode, so it is assumed that the altitude variations are very small, so that the variations in Mach number will be represented by variation in velocity only, because as usual the Mach number is what? The velocity of object by velocity of sound. So here it is directly proportional to the velocity of object only. So here you see in figure 1, a block diagram has been given for altitude mode Mach hold autopilot control system. As the change in velocity is being needed for the outer loop, so the complete 3 degree of freedom longitudinal equation must be used for root locus analysis of both the inner and outer loop. So because here that 3 degrees of freedom longitudinal equations have been using here, then the root locus plots also will be make it for inner and outer loop. So for the aircraft, the transfer function is for Mach hold thing will be like what? Theta dot s by delta es will be equal to minus 1.31 into s into 0.016 into s into 0.3 by s square plus 0.00466 s plus 0.0053 into s square plus 0.86 s plus 1.31 degree second per degree. So I mean generally it is theta is in degree, and here it is also in degree only, but theta dot means that per second how much degrees it is been getting, also that is being controlled by this transfer function only. So because of the short period portion of equation 1, I mean here the short period for thing we will get it by this polynomial equation solution. It is almost identical to short period approximation of transfer function theta s by theta s and delta e by delta e of s. So here you see the block diagram of this one. So here you see that summing this is a summing amplifier, and this is a separate transfer function, and there is an inner loop is there. So there in the inner loop that rate gyro thing also been given here, and there is a separate two two transfer functions also been involved here. So there will be a feedback system that is with respect to EU. So that is with respect to velocity changing. So that transfer function is been given here only. So the remaining, here if the remaining poles and zeros of equation one, like poles and zeros means what? Poles means real values and zeros will be imaginary values. So if it is plotted, then they would be appear as a if located at origin, and therefore it would not be changed with root locus. So since the aircraft gain for the 3 degrees of freedom transfer function is from the short period approximation, so the rate gyro sensitivity will be designed at around 1.98 to 2.1 volt per degree centigrade. Degree second, because rate gyro value with respect to, rate gyro value we are giving as an it is like a feedback thing. So the feedback it is getting from the rate gyro orientation only. It is depending upon the trade gyro orientation. That gyro system will control that how to behave with respect to that control input, control output behavior. So with respect to that, it will take the feedback from there, and that feedback will be fed up to. It will be connected to that summing amplifier. So from that summing amplifier, the input signal also being varied only. So it is still necessary to determine the location of fugite poles for this value of red gyro sensitivity. To do this, the portion of root locus near the origin must be explained, that is in figure 2. So here you see this is actually previous. If you see that red gyro transfer function root locus plot, if you see it on that displacement autopilot time, there we already discussed about this root locus thing, like here that loop root locus, and near to that imaginary values also how it is been behaving. So that we already that we said that one. If you want to remember, if you want to refer that, please refer my previous video. So there it will be like a the pole values are almost constant here, and this imaginary values are being given here. So same as like this here also the root locus plot for that rate gyro function, rate gyro gain is been given here. So that is around 2.1 volt here. So in there we made it for 1.19 to 1.98. So here it will be 2.1 volt. So here that it is showing like to do the portion of the root locus near that origin, it must be it is shown here in figure 2. So here to obtain the portion of root locus in vicinity of the origin, it is assumed that the angle and magnitude contribution from poles and zeros have been shown in that figure. So the closed loop location of that fugite poles have been shown in figure. So there the combining results of figure that 2A and 2B. If you see this 2A and 2B, so I mean 2A and 2B, the closed loop transfer function for inner loop will be around SRG is SRG made it here as 2.1 volt per degree second. So that can be obtained, and the thing closed loop of the closed loop transfer function will be given like this only. So this is the closed loop transfer function thing. So here there is a slight changes to that previous thing only. So see here as far as 0.016 and 0.3 have been given. So here also that is there, but the denominator there is additional values have been involved here. So this is for closed loop that SRG transfer function thing only. So these are the things, and depending upon that, the root locus analysis of that outer loop, if you see that figure 3, so this is the block diagram for root locus analysis of outer loop. So that outer loop root locus, if you make it from here, you can use this one only. So here, as in the case of glide slope, previously that glide slope coupler thing, if you remember, so there the theta dot output of that inner loop must be changed to u. Change it to u only. That means we say it is with respect to that velocity how that glide slope thing is been changing. So the required output for the required output for the outer loop. So that will require like a u of s by theta dot of s. So that is the transfer function which is u times the ratio of us by delta es. So the transfer function to that theta of s by delta e of s will be given like this. So if you see that u of s by theta dot of s will be 0.23 into s minus 68.6 into x plus 0.6 by 53 into s minus 57.3 into s into s plus 0.016 into s plus zero point 0.3. So this is actually the transfer function for the us by theta s. So here the 57.3 in that denominator will be required to convert the theta of s by delta of s from radians to degrees only. So here that this is a constant required to make that radians to degrees only. So from this equation, that previous equation 2 and this 3, so that simplified block diagram for outer loop locus have been shown in previous figure. So this is figure 3. So this is the transfer function. It has been operated for u and theta. So for that the outer loop thing, this outer loop thing, if you remember this, so it has been came from here only. So the total inner loop is been converted into that, and that with that the outer loop feedback also, with the outer loop feedback also, what will be the block diagram will show. So that is shown here. So here the due to that zero in the right half plane of that forward transfer function, that is zero in right half plane of transfer function, the steady state sign of u for a positive input is positive only. Here you see that zero in the right half plane of forward transfer function, that forward transfer function is being given here, no. So due to that steady state sign of u for a positive input is generally positive value only we will get. So therefore the minus sign is here the minus sign will is required to summing of the feedback signal only, and the zero angle root locus must be that zero angle root locus have been given here. So that has been shown in this figure 4. So this is for root locus of outer loop of Mach-Hold mode. So that is the zero angle root locus. So here that SU, that value SU is been taken as that means here you see that SU value. So this the SU value considered here is 1.19 volt per volt only. So as the poles move to the move towards the right half plane at the same value, SU dash SU dash there will be closed only. So because if it is going the right of plane, the right side of that plane, so the SU dash value if you consider, so that will be near to closing value only. So this is the response of Mach-Hold control system at a step input of S of SU will be at 1. So this is like the with respect to that small changes in the u, alpha, theta, gamma, and u of u reference values. So how that the mode shapes have been considering, and how that are been changing also will see here. So here you see the change in mode shapes are generally with a small change in Mach-Hold thing. So if you give small velocity, that velocity will be gradually decreasing and after that it is getting constant only. So if there is a change in alpha is there, that alpha prime is there, then there will be a small damp, and after that it is getting constant only. Also for elevator angle theta also it will be like almost constant only. And for the gamma, that rotational angle is there, lateral angle displacement is there. Then there also there will be a small damper was happened. After that, it is getting constant only, and the reference values are always made it as almost constant. There is a sudden decrease. After that, it will be C only. So these frequency plots, that frequency response plot will gives you that when you are giving that input to that input to that autopilot system, so the due to that output of that autopilot system, how that total values have been, the total aircraft behavior will be, how it will be generally we can know. So that for that reason only, these response diagrams will be made. So here you see that altitude hold mode of control system. So previously we discussed about Mach hold control system, and now it is a altitude mode control system. So here you see, so that one reference values we already given to that given as a input to that summing amplifier. So from there the input to that transfer function has been given here, and after that there will be one inner loop also there. So that inner loop is been having one transfer function, and the dynamic control system also been here. So from there that output is being given as a, this h value will gives you the actual output, actual output, that is altitude, the height only, that height of aircraft only. Height means altitude of aircraft only. So here there are two that feedbacks also, that rate gyro feedbacks, and the transfer function also been fed up to that summing amplifier. So here you see that loop location determines the degree of stability of the system. So poles near to that origin representing the phugoid mode move around. So that will be break into real axis and that dominant routes only. So if you see that the response of that system to a step command U reference, that U reference means that what will be the actual value, it has to make it as a reference value. So that has been shown in figure 5. So if you see that figure 5, that U reference values have been given here. So the dominance of real poles near to the origin is evident, especially in the velocity response. So the fact is that the velocity response exhibits a pure first order response characteristics, and that the steady state condition is reached in 40 seconds, suggest an almost ideal response only. So so this block diagram will gives you the altitude hold mode that has shown in the previous thing. So as in case of acceleration control system, if you see previously, the short period approximation can be used for analysis of altitude hold mode only. So the jet transport is being used for this analysis. The root locus of inner loop is the same as shown in that previous 2A, 2B, that is Mach hold thing also. There also the outer loop thing is same only. I already told now. So this is the outer loop transfer function. So here the rate gyro has been established at 1.98 value only. So for this, the transfer function theta of S by E, that is with respect to, with that altitude hold. So this is depend upon this transfer function. So so here you see the block diagram for that outer loop analysis is being drawn in this figure. So the minus sign appears that hs by delta s. So this is delta s only. So the transfer function arises from a sign convention, and the gamma, this is a gamma only. So they both are gammas. So the gamma is taken as a positive. Here the H is considered as positive for aircraft whose altitude have been increased. So this is also consistent with measurement of altitude only. So see here for outer loop separately how that transfer function is being designed here. So here that AZ, that AZ is given here, no. So that is aged will be that aged will be taken as a positive downward. So that there the H will be equal to -1 by S square into aged. So this is a sign at the summing amplifier for feedback cycle must be negative for same regions as these discussions will be in the acceleration control system only. So the zero angle root locus, the altitude hold mode can be seen in this figure 8. So with the location of the closed loop, the ports at SH will be make it as 0.43493. So here that the transfer function it has been depend upon will be that hs by theta dot s will be equal to -1 by s cube into az of s by theta of s. So that will be equal to this value. So that is -0.135 into s minus 4.89 into s plus 4.89 s square into s plus 0.306. So here that same if you see that root locus plot for previous that outer loop also how it will be, so that only, but here there is a small asymptotic relation with respect to that real axis. So this is also for zero angle thing only. And then that response of altitude mode have been given here. So this is a response of mode for u alpha theta and gamma h and h reference. So here also while we are giving that input to that altitude mode, whether if that control system is giving very less damping only. So this damping will be slight changes only. But if there is a big change, if you are giving for a H means, so there will be a linear variation if you see here. So there is a linear variation is going on. But in gamma and H reference will be almost very less damping thing only we are getting here. So here it is possible to control the flight path angle without simulation, without simultaneous control of the velocity. That means flight path angle will be controlled with simultaneous controlling velocity also. So therefore, although the short period equations are used for analysis, the complete 3 degree of freedom equations are employed for simulation that is being combined with velocity control system, and that will be used for glide slope control system also. So here everything is interlinked only, and the response of that altitude hold mode is been shown in the previous figure. So for the step input of 100 feet per hour, for a H reference, so the value is equivalent to that engaging altitude hold mode with an error of 100 feet between that actual and the reference altitude only, because there may be some 100 feet error may be there. So as we can see from the computer traces that the root locus plotter, so a plot only will gives you the simulation results. So the change in altitude is smooth with no violent change in angle of attack or pitch altitude. So this discussion will gives you the complete analysis of two modes of flight path stabilization only. So that means here you can see while we are considering about that flight path stabilization, and flight path stabilization is mostly depending upon that Mach hold and altitude hold only. So here that there will the computer simulation for making this design of this autopilot system. So that the simulation results, how we can know? We can know by that response figure behavior and that root locus behavior only. That root locus behavior will gives you where the values have been given. It is going to real values or imaginary values. Imaginary values means how it is going. That imaginary values will be giving you that change in the changes in that output values will be more. So that means here the simulation results will gives you that frequency response. That frequency response will gives you the behavior of that aircraft while we are giving that input only. So this is showing that when the change in altitude with a smooth, I mean, if the change in altitude is smooth means what? The gradual variation is there in, if it is there in altitude, so there will be no changes in angle of attack or pitch altitude also, because it is a common sense only. While you are giving a sudden angle of attack, then it is not like a fighter jet. I mean, if it is a fighter jet, the sudden angle of attack will be there, sudden altitude changes will be there. But for passenger aircraft, these type of sudden things are not recommended. So there will be anything will be like a smooth operation, that too a gradual increase only. So that gradual increase only will gives you how to make that. I mean, how to make that operate that autopilot system very smoothly and without any way deviation in stable deviation in the stability also. So this is all about this flight path stabilization. Hope you understood, and hope you get some good points about this one. So if you have any further queries, you can refer this Blake Rock textbook and the Stephen BL textbook also. So for the further clarification, you can refer these books. So that's all about this flight path stabilization. So next class we will see some more interesting topics on coming classes. So that's all about this. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.